recording yet. Well, now I started. Okay, so practically you can actually also handle the this rounding effects on this one, which is a good place to actually do the design. Since there you can also take a look at the different kind of architecture, filter architectures to select the one that fits your application the best. Anyways, let's start with this, for example, IIR filter, elliptic. Let's mark the FS, for example, at FS what we had. Then we have passband 100 Hertz and stop band at 200 Hertz, for example, like, and design the filter which looks like that. Okay, how does this filter actually work with different quantization? First of all, the structure here is direct form to second order sections. By default, all these IIR filters are actually structured like second order system the filters, because these are more vulnerable for these calculation errors, where the errors actually can make these unstable easily. Okay, so that's why the design is like that. We can also take a look what happens if we change this design. But anyways, there is the box there saying set quantization parameters. Do you have the same tool there? Good. Click that one. Now we can take a look what happens if we change the filter arithmetic. How does it go with the single precision floating point? Still the same. Floating points are pretty good actually. There's plenty of room for different size, different magnitude values, and the calculations are close enough. Usually they are going between double and single precision on real life filters. It's not a biggie. You just use single precision wherever you can, unless you have double precision floating point units. Okay. With modern processors, usually you can use parallel to the single precision floating point units instead of one double precision. So it's actually split in two halves. So I would go with this single precision. Or actually, I would first go and read the manual. Okay, the fixed point is the more interesting thing. Okay, there we have coefficient word length 16 bits, and we still are pretty good on this filter. So basically this is exactly the same line, low pass elliptic quantized and then low pass elliptic reference. Both are the same. We can then fiddle around, for example, to try 8 bits. What happens? 8 bits. Okay, we get some difference here. Maybe 7 bits gives more. Yeah, 7 bits, but it's still usable when we are using this second order system architecture. Let's go back to the 16 bits and do something else here. We will do something stupid. What you never should do. But I will just show you. You can actually analyze this one. How about if I convert this one to single section? So only BBs and AAs, only one vector of each. Sounds like it's easier to implement No, it's not. Then basically, yeah, you have one function. But how hard it really is to make actually three or one second order system function, just fiddle the parameters there. It's that would be saving on wrong place, but let's see. Ah, it's still about the same. That we got lucky. Murphy wasn't here. But anyways, you already can see that on passband there are some difference. This is fixed point. Fixed point 16-bit precision, sixth order filter, which means we have the on denominator parameters we have over the 2 power 6 quantization level. Well, 16-bit. No, sorry, not I'm blabbering here. So we have around, yeah, enough of change. But anyways, if we go here, oops, sorry. If we here go and fiddle the coefficient length and try, for example, 8 bits, my guess is that does not work anymore. No. If we use 8 bits word length on this quantized, what we also got, look at the stability. It's not stable anymore. We got one of those poles actually outside of the unit circle. Yes, actually, 3 of the poles are now outside of the unit circle. Okay. So let's see when we have 10 bits accuracy. No. So maybe 14 bits accuracy. Yeah, now we have the, it's stable, but still the, I think these amplitude responses are not quite the same. No. It's marginally usable with a 14-bit resolution. Lower resolution gives you unstable system. Okay. And basically the denominator parameters give you the idea why that happens. See, this quantized denominator actually have the biggest number is 12 and the smallest number is 0.6 on denominator. So it's basically so that's almost 3 orders of magnitude different. That's a lot. So small errors there make a huge difference on the performance. Okay. That's not interesting. Okay, but anyways, that's how you play with this fixed point arithmetics, and okay, you can play it with the also with the second order system. Let's see, does it do the same thing again? All right. Fixed point. Second order systems again. Now this is totally, you know, it's not the same anymore. Okay, there we go. So, yeah, that's how you use the filter designer to check these how many bits you need. Let's go back to the exercise and see what I'm actually asking you to do. So what's the beef here? Okay, first one is making the same notch filter as you did on exercise 5. And then check if it works with 8 bits arithmetics. Easy. Actually, the filter designer is also can be used for that one. I think you can design a system based on the zeros and balls. Or was there actually a bandstop notch filter on filter designer? Bandstop? But actually, if we specify order as second order, I think that then actually might be a notch bandstop. Let's see what happens. It's notch filter. Haha, hey, see, it actually is a notch filter when you define the order to second order. Yes, is 100. 100 minus 10, 90, 110, design filter. Yep, that's the notch. You can check what happens to the filter then using that. Okay. And what happens to stability, not frequency change, attenuation at original notch, meaning what is the current attenuation at the filtered frequency? What happened to the bandwidth if you can define it? If it goes to unstable, it's irrelevant what is the bandwidth since you cannot use it anyways. What happened to the bandpass ripple and such kind of thing? Well, ripple doesn't change much, but it will change the bandpass characterization. Okay, then third one, you will design a bandpass filter. I think this could be the same as on the fifth exercise again, but then you basically fiddle around with the on finding out how many bits should be used if the system was implemented as a direct form filter on a fixed point system. No second order section, the single section system. So basically, just check where you think is the kind of the level of quantization you can tolerate, or this system can tolerate. Then the same thing for implementation for the second order system. You might actually want to go with the second order system first, since you will get the second order system there first, and then the first order system, or the direct form single section. Single section. Okay, and yeah, check those. And I would guess that on second order system you get similar results what I saw there. So you can actually have less bits for calculations. Okay, about the data, of course, if you have 24 bits of data, you don't want to quantize too much of that one. But it makes a big difference if you can use 8 bits multiplication on 24-bit data, then it still fits into 32 bits without overflow. Okay. But 8, how many multiply accumulation operations that would take on, okay, it says the, on how many bit system, and then how many channels a Cortex M3 running at 120 megahertz can approximately manage running the previous filter. Was it Cortex M3 on these boards or Cortex M0? Which one? M3, I think it's M3, and 120 megahertz probably. Maybe. Yeah. So yeah. Okay. You can localize this one to that board. So how many channels on a Cortex M3 running whatever, or Cortex M, which M3, yeah. Okay, and then they usually 120 megahertz. Yeah, so basically estimate how many channels. The last one is fun. Measure the performance of your laptop and estimate how many channels it can handle on MATLAB. I will show you how to do it. So this gives you also a hint. If you are really into the embedded systems programming, you can always guesstimate that. On some of the standard C++ libraries, there are these timing operations that you can actually get the millisecond timer reading at the moment. So what you can do is just take the time, system time before the filtering, and then run the filtering, say, few thousand times maybe on a loop, and then basically measure the time it took. And then you can calculate how many samples it can manage in certain time, which gives you the estimate of how many channels you can actually filter during using that system. On MATLAB, I'll show you how to do the performance calculations. I have the filter AABB here. That's very interesting filter, but anyways, one way of doing it would be to have random data, enough of samples, 44,100 samples. Actually, let's do it like that. 44.1 thousand samples. That would be a sampling rate of okay, how many channels? Let's make it this audio channels at fs equals 4400. Yeah, audio channels. It doesn't actually say which channels and what is sampling rate. Okay, so so that basically 1 second long random audio sample. Right. On computer, with filter BBAA, it takes about 1.4 milliseconds to actually run through that one. If you run this few times, then you can actually see the where it's more or less settling. So basically, it settles somewhere around 0.6 milliseconds. So basically, then time, how many channels of that kind of data you can. Okay, about 2,000 channels. That's how easy it is. You just calculate what is the time it takes for to analyze one single channel data, and then estimate from that one. In this kind of estimations, the brute force usually gives you the most reliable results, because it also takes into account the overhead. As you can see, this command, depending on what time it is run, the first time you call the function, any function, it takes longer time in MATLAB then basically it's the function itself. When you have called it, it's already downloaded to the working memory. So this kind of virtual virtual memory machines, the best way to estimate the performance is by brute force, by measuring it. Yeah. Okay. I think that's all for today. Where did I put my... There. Okay, good. So, band stop knots filter, determine filter coefficients. Oh, hey, wait a minute. I'll change that one to 22. So it basically it's the same sampling rate as on this exercise. Otherwise, makes more sense this way. Yep. Good. Any questions?